Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to the course on advanced transition metal organometallic chemistry. We have been discussing transition metal arene carbonyl complexes. These are half sandwich complexes and also have different different reactivity as well as structure and bonding. With respect to these transition metal arene carbonyl complexes, we have looked at structures they exhibit, which can be the conventional eta 6 mononuclear metal carbonyl complexes to that of eta 2 bound dinuclear metal carbonyls or eta 2 bound trinuclear metal carbonyl complexes. We have also looked into the reactivity pattern of these arene metal carbonyl complexes, and what we had discussed is the fact that electrophilic substitution reactions though occur, but occur at a slower rate as compared to that of free arenes, and this has been attributed to the inductive effect of the metal carbonyl bound to the arene ring. In as opposed to the electrophilic substitution reactions, the nucleophilic substitution reactions, however, are more facile for these arene metal carbonyl complexes. The nucleophile attacks on the ring from an extrovasation, resulting in the loss of aromaticity followed by the loss of the leaving group from the endo site, which we had taken looked at an example for which the endo loss of the chloride ligand was the rate determining step of these reaction. We have also seen as a part of this reactivity that these arene metal carbonyl can also be substituted by sigma donor pi acidic ligands at elevated temperature. Continuing further along our discussion on these metal carbonyl arene complexes, we would look at the oxidation reaction that usually is observed. Now, this oxidation reaction is kind of unusual in the sense that oxidation of 18 valence electron compound does not result in a oxidized 17 electron species, but instead produces an 18 valence electron compound with a different anion, and I will sort of explain that with this example over here. So, oxidation of 18 valence electron complex does not yield 17 valence electron radical cation, but results in an unusual anion, and this is illustrated by the example over here. Eta 6 arene molybdenum tricarbonyl, which is a 18 V complex with iodine giving eta 6 arene molybdenum tricarbonyl iodide plus and a corresponding anion, which is Me2I5 CO6 anion. So, this is a interesting example that gives that the oxidation does not lead to the usual 17 valence electron radical cation, but results in a very unusual kind of anion which is shown over here. Now, the other interesting reactivity is the shift of eta 6 to eta 5 hapticity. And so, this example would involve eta 6 to eta 5 shift of chromium tricarbonyl fragment, and this is beautifully explained in this reaction. CH2 chromium CO3 reacting with KH THF minus 30 degrees centigrade eliminates hydrogen to give this benzene ring bound chromium CO3 and this anion, which in 30 degree centigrade undergoes the shift to give eta 5 bound chromium CO3 minus, which in presence of Ri eliminates I minus, giving the alkylated chromium R CO3 that at 50 degrees centigrade gives back the original eta 6 bound chromium carbonyl R. So, what is observed over here is that it is a demonstration, a beautiful demonstration of eta 6 bound arene chromium carbonyl compound giving rise to eta found by species, and then it again goes back to eta 6. So, this is eta 6 to eta 5 and then back to eta 6 reconversion. Very nice example is shown over here. Another such eta shift involves going from one eta 6 ring to the other eta 6 ring. So, the previous one was going from eta 6 to eta 5 back and forth, and the subsequent example that you would see would involve shifting from eta 6 to eta 6. So, this is eta 6 to eta 6 shift of chromium eta 6 to eta 6 shift of chromium tricarbonyl fragment, and this is beautifully illustrated by the example over here. If one of the benzene is deuterated, chromium carbonyl at 130 degree centigrade, giving deuterated chromium carbonyl. Now, this shift from one of the ring to other only occurs at elevated temperature. Now, here is another two interesting reactions which are widely spoken about metal arene complexes, and these can be of metal arene Ln type of complexes. So, these are of the type eta 6 arene metal Ln type complexes, and some of the two such examples are given over here. The first involve preparation of these complexes from let us say magnesium in presence of 2 C6 F5 Br, and this was co-condensation method in presence of C6 H5 Me, then M Br2 is lost, giving rise to this benzene substituted metal C6F5 ligand type complexes, and M equals cobalt and nickel. So, this is the co-condensation method involving Meng in the gaseous state with pentafluorobenzene bromide in presence of methyl benzene leading to the formation MBr2, and this aryl aryl complex which sort of in presence of arene loses the benzene to give eta 6 arene metal C5 C6 F5 whole 2 type complex. So, one can see that the co-condensation method or metal vapor synthesis method is successfully used in synthesizing aryl arene eta 6 arene and C6H5 bis Ln type complexes. So, here is an interesting example. Another very interesting example we are going to be talking about that can be used for preparing wide variety of complexes, and one such reaction is the reaction of this cyclohexadiene plus ruthenium trichloride in presence of ethanol gives this dimeric compound that with silver chloride and Na2SO4 and sodium carbonate giving this compound. This is ruthenium tetrameric hydroxo compound, bridging hydroxo on each of this ruthenium. This is OH, and each of this ruthenium is bound to 4 benzene rings. There is one over here, and this one is bound to one benzene ring, and this ruthenium is bound to another benzene ring. So, this gives this tetrameric compound, which can be written as eta 6 C 6 H 6 ruthenium 4 OH whole 4 plus. So, this is a interesting cubane kind of compound. The reaction of this ruthenium dimer with L breaks the dimer and produces the corresponding monomeric compound. L can be P R 3 CO. If one abstracts the halides with AgBF4 acetone, then twice AgCl results, and one gets a interesting acetone adduct of this compound. Two plus and 2BF4 minus, which reacting with cyclophane gives a bis dinuclear compound, interesting dinuclear compound. Bis arene kind of dinuclear mixed cyclophane benzene ruthenium compound. Four plus, and what one sees that these arene ruthenium Ln kind of complexes can be used to produce a wide variety of interesting compounds, not only in terms of formulation, but also in their rich structure and diversity. And one can see this tetrahydroxybent cubage ruthenium tetrameric structure, or the monomeric ruthenium halide phosphine compounds, or this interesting ruthenium acetone adduct with this huge mixed bis arene cyclophane benzene kind of dinuclear ruthenium compound. So, this is really some very interesting chemistry exhibited by this compound. And one thing which comes to the fore is the fact that these arene ruthenium dicationic species C6 H6 Ru plus 2 plus is resistant to hydrolysis, hydrolytic cleavage, and because of which these kind of complexes, ruthenium complexes, have been found to be very cytotoxic in nature. So, they have anti-cancer activity because they do not get hydrolyzed, and this one such compounds which is eta 6 arene ruthenium X ethylenediamine plus or 2 plus, okay. X can be chloride or water are cytotoxic against cancer cells. Including the cisplatin resistant strength. So, this is a wide very interesting application of ruthenium eta 6 arene complexes, that they not only can form interesting structures, but they have also, because of their resistance to hydrolysis, they have found use as very good anti-cancer agents, and not only that, they are also quite active against the ones which are which cisplatin now later on becomes ineffective, or these ruthenium compounds are active against cisplatin resistant strain as well. So, with this we are going to just briefly finish upon the structure our discussion on arene metal Ln type complexes, and we move on to something which are more interesting or more intriguing, and these are heteroleptic bis arene transition metal complexes. To be more precise, we are going to be now talking about benzene cyclopentadienyl complexes. So, eta 6 eta 5 bound heteroleptic bis arene kind of complexes. So, the next few minutes of this lecture would be dedicated to benzene cyclopentadienyl complexes, and these are complexes with both 5 and 6 membered rings. This is beautifully illustrated by reaction MnCl2 plus Na C5 H5 plus C6 H5 MgBr reacting with THF to water to give Cp Mn C6 H6. So, the thing which is notable of this fact is that the yield of the reaction is only a 2%, and the major product formed in this reaction is biphenyl Mn C5 F5. So, the major product is biphenyl Mn C5 F5, which is about 15%. And there are several other byproducts of the reaction. One is this biphenyl bis manganese cyclopentadienyl, so that is 3%. So, that is also a very interesting compound, biphenyl manganese Cp is 3%. Okay. So, one thing which comes out that in this method all possible compounds are formed, and the compounds which are of the interest, the desired compound is formed only in 2%, and there are other compounds, for example, biphenyl manganese Cp 15% or biphenyl dinuclear manganese Cp only 3% can be formed. So, these reactions can also be used for making the chromium complex, but here also the corresponding chromium complex by the same method which gives benzene chromium cyclopentadienyl. This is a 17 valence electron compound, and by this method this is formed in only 3%. So, this method, even though it produces the desired compound, but what is evident from here that the yield of the reactions are indeed very little, which can be about 2 to 3%. So, with this I would like to draw a conclusion on today's lecture. Particularly, we have looked at the reactivity of transition metal arene complexes, and to begin with we have looked into these 3 new kind of reactions. The first one being the oxidation reactions of arene transition metal carbonyl complexes, and what we had seen that it does not really give the desired 1 electron oxidation given in the 17 valence electron species, but forms an unusual counter anion of molybdenum. Then we had taken 2 other examples where we had seen a reversible shift from eta 6 to eta 5 hapticity in arene systems, where it goes from a 6-membered ring to a 5-membered ring, and then we had seen another example where it went from 6-membered ring to another 6-membered ring under elevated temperatures. In addition to that, we have also looked into other types of transition metal arene Ln type of complexes, and these we have looked at from perspective of 2 reactions, the first one being the formation of these complexes which leads to arene metal bis C6F5 type complexes, and the next one we had seen are the reactivity of arene metal halide kind of complexes. And what we can see is that these complexes, depending on the reagents used and the halide abstractions taken, they can give rise to many other interesting compounds. For example, we had looked into the Cuban type hydroxo bridge arene ruthenium tetramer, and also we had looked into this mixed cyclophane arene mixed dinuclear ruthenium complexes. We have also discussed that these arene ruthenium dication species are resistant towards solvolysis, and because of which has been exploited in making very good cytotoxic compounds that not only was cytotoxic against cancer cell lines, but also against cisplatin resistant cell lines. Now, we have finished in this lecture on this arene transition metal carbonyl as well as L type complexes, and then moved on to discuss these new types of benzene cyclopentadienyl complexes, and we have looked into the first synthetic method, and what we saw that this method is not very selective and also very poor yielding in terms of the desired compound, which could only be isolated in about 2 to 3% yield in presence of other mixtures which were up to 15% yield. So, this speaks about the challenges in isolating this kind of mixed heteroleptic transition metal bicyclic type complexes. So, more of their synthesis and further discussion will come up in next lecture, and I thank you for being with me in this lecture, and hope to discuss this in more details when we take up this topic in next lecture. Till then, thank you and goodbye.